Winter, 1941. The Atlantic is steel gray and unforgiving. Across Europe, airfields thrum with engines pushed to their limits, British Spitfires clawing for altitude, German Messerschmitts screaming through cold air at full boost. The war in the sky has already revealed its brutal arithmetic. Speed is life, altitude is advantage, and power decides who comes home. The United States watches from across the ocean, officially neutral, materially confident. On paper, America appears unstoppable. Vast oil reserves, unmatched industrial capacity, factories capable of turning out aircraft by the thousands. Yet beneath these numbers lies a vulnerability so fundamental that it rarely appears in doctrine or public debate. America does not yet possess sufficient quantities of the fuel required for modern air war. At the dawn of the 1940s, aviation has changed faster than the institutions meant to support it. Aircraft engines are no longer simple machines. They are precision instruments, supercharged, stressed, and optimized to extract every possible ounce of power from combustion. To do that safely, they demand gasoline of exceptional quality, fuel with high resistance to detonation, measured by a number that rarely makes headlines: octane. In Europe, this lesson has already been paid for in blood. During the Battle of Britain, the Royal Air Force quietly introduces 100-octane fuel, allowing its fighters to operate at higher boost pressures within carefully defined limits. The change is subtle but decisive: improved climb rates, tighter turns, and a narrow margin of power when it matters most. German pilots notice. British engineers document the results. The war moves on. In the United States, the implications are slower to land. American refineries in 1941 are among the most productive on Earth, but they are built for a different world. They excel at producing automobile gasoline, diesel, and heating oil. The dominant industrial processes, thermal cracking chief among them, can deliver volume, but cannot reliably produce high-octane aviation fuel above the low 90-octane range at the scale modern air combat demands. For peacetime flying, this is sufficient. For sustained high-altitude combat at full throttle, it is not. This mismatch begins to concern American planners in the months before Pearl Harbor. The Army Air Forces are designing aircraft that promise extraordinary performance: the P-38 Lightning, the B-17 Flying Fortress, and other prototypes that hint at a new era of range and power. But engines, no matter how advanced, can only perform within the limits imposed by the fuel that feeds them. A senior engineer at Wright Field would later recall the unease of the moment. We had the airframes, we had the engines. What we lacked was operational margin. That margin is fuel. In Washington, strategic attention remains fixed on ships, steel, and manpower. Fuel quality is treated largely as a technical issue, not yet a strategic one. In laboratories and refineries, however, a quieter conflict is already underway, fought with pressure gauges, catalysts, and fractions of a second inside combustion chambers. The stakes are no less severe. Oil executives and chemical engineers understand the problem in precise terms. High-octane aviation gasoline is not simply better gas. It is the result of molecular structure, branched hydrocarbons that resist premature ignition under extreme pressure. Producing it consistently requires methods that go beyond heating crude oil until it fractures. It requires control, selectivity, chemistry. Some of that chemistry already exists, scattered across patents, pilot plants, and experimental facilities. In the 1930s, catalytic cracking, using solid catalysts to reshape hydrocarbons rather than brute heat, has shown promise. Eugene Howdry's work demonstrates that octane and efficiency can be raised simultaneously. What remains uncertain is whether such methods can be expanded fast enough to meet wartime demand. By early 1941, America's strategic outlook sharpens. Germany dominates most of Europe. Britain remains in the fight, but at high cost. Japan advances across Asia, its naval and air forces fully fueled and operational. If the United States enters the war, as now appears increasingly likely, it will fight across oceans and continents. Air power will not merely support operations, it will underpin them. Yet that foundation remains fragile. A memo circulating within the petroleum industry that spring notes a sobering reality. Current U.S. production of true 100-octane aviation gasoline is measured not in millions of barrels, but in thousands. It is a trickle. Against the projected requirements of a global air war, it is strategically insignificant. Here, the central tension of America's coming war effort becomes clear, not between courage and fear, but between innovation and institutional habit. A nation accustomed to abundance confronts the limits of that abundance. Volume alone is no longer enough. Quality matters, precision matters, and time is becoming a constraint. On December 7, 1941, the problem ceases to be theoretical. Pearl Harbor burns. The United States enters the war. Aircraft scramble, engines roar, and the demands placed on American aviation expand overnight. From planning tables to combat reality. Every additional pound of boost, every extra mile of range, now carries lives with it. The fuel problem can no longer be postponed, debated, or compartmentalized. Somewhere between the oil fields of Texas and the engineering offices of New Jersey, between chemists who think in molecules and pilots who think in altitude and speed, a shift is taking shape. It is not yet a solution, but a recognition, one that will transform the American petroleum industry and quietly alter the balance of air power. The war will be fought with bombs and bullets, but its outcome will depend in part on what burns unseen inside an engine at 30,000 feet. Spring 1942. The war expands faster than anyone predicted. Across the Pacific, American aircraft operate from coral strips carved out of jungle. In the skies over Europe, British bombers push deeper into occupied territory, escorted by fighters already operating at the edge of their endurance. Everywhere, engines are being asked to do more than they were ever designed to do: climb higher, run hotter, remain airborne longer. Pilots feel the limits first. At altitude, the air thins and the margin disappears. Throttles ease forward, superchargers whine, and engines begin to knock. An ugly metallic rattle every pilot recognizes as danger. Detonation is not dramatic. It does not explode. It destroys engines quietly from the inside, shattering pistons, warping valves, ending missions before they truly begin. A fighter pilot in England writes home in early 1942. She wants to give more, but you can hear her complaining when you push it. What he is hearing is chemistry. Behind the front lines, American engineers confront a constraint that production figures alone can no longer conceal. The United States can build aircraft faster than any nation on Earth, but speed, range, and reliability are being capped by a factor rarely visible in combat footage: fuel quality. At refineries across the country, men in hard hats and lab coats now work under conditions increasingly governed by wartime priorities. Profit margins give way to performance requirements set by military planners. Every incremental gain in octane translates directly into additional power, endurance, or survivability in the air. The breakthrough does not come from a single invention, but from a convergence: technical, industrial, and organizational. Catalytic cracking, once experimental, is pushed into full industrial service. Unlike older thermal methods, it employs solid catalysts that promote specific molecular rearrangements without being consumed. Heavy hydrocarbons are broken and reshaped into lighter, more stable compounds. The result is gasoline with higher octane and far greater consistency. But catalytic cracking alone is insufficient. Engineers layer solutions deliberately. Alkylation units combine light gases into dense, high-octane blending components. Isomerization converts straight-chain molecules into branch structures that resist detonation. Tetraethyl lead, already controversial, is added in controlled quantities to suppress knock under extreme operating pressures. Each process addresses a specific limitation. Together, they form an integrated fuel production system rather than a single technological fix. By mid-1942, refineries operated by Standard Oil of New Jersey, Shell, Texaco, and other firms, working under coordination with newly established wartime petroleum authorities, are redesigned almost in real time. Blueprints are revised while construction crews work beneath them. Units that once required years of planning are completed in months. The scale is unprecedented. This is not innovation for its own sake. It is innovation under constraint. Steel is rationed. Skilled labor is scarce. Errors carry immediate consequences. An unstable catalyst bed or mismanaged reaction can halt production for weeks, grounding aircraft thousands of miles away. Yet the pressure to deliver never eases. The war in the air allows little forgiveness. In England, American bombers begin sustained daylight operations over occupied Europe. The B-17 Flying Fortress, bristling with defensive guns, is a remarkable design, but its effectiveness depends on maintaining tight formation at altitude, engines operating at high power for hours at a time. Early missions reveal the limits. Aircraft fall behind, engines fail, crews are lost, not to enemy fire alone, but to mechanical constraints. Each loss echoes back across the Atlantic. By late 1942, the first measurable results of the refinery effort appear. Supplies of true 100-octane aviation gasoline increase significantly, not yet in abundance, but enough to justify cautious changes in operating doctrine. Pilots are authorized higher manifold pressures. Engines are tuned more aggressively within defined safety margins. The aircraft feel different. A test pilot notes the change after refueling. Same airplane, not the same climb. This is the invisible advantage. Enemy pilots cannot see it. Intelligence officers struggle to quantify it. But operational reports begin to show consistent trends rather than isolated anecdotes. American fighters remain with their formations longer. Bombers hold altitude more reliably. Abort rates decline. The effect compounds. As fuel quality improves, engine designers respond. Power settings once restricted to emergencies become routine. Maintenance schedules adapt. Confidence grows, not bravado, but measured trust in the machine. That trust rests not on pilot skill alone, but on fuel engineered thousands of miles from the front. The war enters a phase in which doctrine increasingly follows capability. What was once a limitation becomes an assumption. What was once a risk becomes standard procedure. And still, the work continues. By early 1943, production of high-octane aviation fuel reaches levels unimaginable 2 years earlier. The United States is no longer supplying only its own forces. It is fueling Allied air operations as well. Tankers cross the Atlantic carrying gasoline, whose specifications are monitored as closely as any weapon system. Yet the ultimate test remains ahead. New aircraft enter service. Missions grow longer. Fighters will be required to escort bombers to distant targets and return. Engines will operate near the edge of their design limits for hours at a time, deep over enemy territory. Whether they endure will depend not on courage alone, but on the industrial and chemical systems that sustain them. A shift is underway, not sudden, not decisive by itself, but cumulative. The turning point is no longer theoretical. It is approaching. Winter 1943. The skies over Europe are no longer contested. They are contested relentlessly. American bombers now fly deep into the Reich, Schweinfurt, Regensburg, Bremen. The names are chalked onto mission boards, each one farther than the last. The doctrine is daylight precision bombing, tight formations, mutual defense, discipline under fire. It is a doctrine that assumes engines will endure sustained stress at altitude. For months they did not. Early raids exact a brutal price. Aircraft lag behind formation. Escorts turn back early. Bombers, heavy with fuel and bombs, are forced to operate at power settings that leave no room for mechanical weakness. Enemy fighters wait patiently, knowing the stragglers will come. By the end of 1943, the margin begins to change. The change does not appear on reconnaissance photographs. It is not announced in speeches or directives. It is felt in the cockpit, when a pilot advances the throttle and the engine responds not with protest, but with predictable performance. High-octane fuel has reached operational maturity. The numbers tell part of the story. Aviation gasoline rated at 100-130 octane is now standard for American combat aircraft in Europe. Engines are cleared to run at higher manifold pressures for extended periods under defined operating limits. Power outputs increase without a corresponding rise in failure rates. What was once an engineering possibility becomes a repeatable operational condition. In January 1944, long-range escort becomes viable. The P-51 Mustang, fitted with the Packard-built Merlin engine, enters combat in strength. It is an aircraft designed around aerodynamic efficiency, laminar flow wings, streamlined fuselage, but its full performance envelope depends on fuel capable of supporting sustained high-boost operation. On 100-octane gasoline, the Merlin can safely run at power levels that transform the aircraft from competitive to dominant. Pilots notice immediately. A Mustang pilot writes after his first deep escort mission, "We stayed with them all the way. That never happened before." For bomber crews, the difference is measured in survival. Engines run smoothly at altitude. Formations hold. Abort rates decline. The long climb to cruising height becomes less punishing. The aircraft remain vulnerable, but no longer fragile. The Luftwaffe, facing this shift, struggles to respond. German fuel supplies are already under severe strain from Allied bombing and dependence on synthetic production. High-performance engines demand fuel that Germany can no longer provide in sufficient quantity or consistency. Power settings are restricted. Training hours are reduced. Mechanical caution replaces tactical freedom. The gap widens, not suddenly, but steadily. The moment of truth does not arrive in a single battle. It arrives through accumulation. By the spring of 1944, American airpower achieves a condition it has sought since the war began: sustained operational superiority. The cost remains high. Aircraft are lost. Crews are killed. But the balance of attrition shifts irreversibly. Fuel has become a force multiplier. Behind every successful mission lies an industrial system operating at continuous strain. Refineries in the United States run around the clock, producing aviation gasoline to specifications measured in decimal points. Quality control is relentless. Consistency matters as much as volume. A single flawed batch can ground an entire unit. The men who produce the fuel rarely see the aircraft it powers, yet their work is present in every engine that climbs past 30,000 feet without knocking, stalling, or failing. On June 6, 1944, the sky over Normandy fills with aircraft. Fighters sweep ahead. Bombers strike inland. Transport planes drop paratroopers into darkness. Thousands of engines operate at sustained high power for hours at a time. They hold. The invasion succeeds not because of a single factor, but because multiple systems align: planning, courage, deception, logistics, and air power. Fuel is one of these systems, doing its work silently, without ceremony. By the time Allied forces break out of Normandy, the war in the air is effectively decided. German aircraft continue to fly, but under constant constraint: limited fuel, restricted power settings, and shrinking operational margins that no longer apply to their opponents. The industrial gamble has paid off. What began as a quiet vulnerability has become a durable advantage. Innovation, driven by necessity, coordinated at scale, has altered the balance of air power without ever appearing in a combat communique. The war will continue for another year. The cost will remain immense. But in the skies, the trajectory is no longer in question. Summer 1945. The engines are finally quiet. Across Europe and the Pacific, airfields that once roared day and night now lie under open skies. Aircraft stand in long, orderly rows: Mustangs, Fortresses, Liberators, paint faded, metal scarred but intact. For the men who flew them, the war has ended. For the systems that sustain them, a different transition is beginning. Victory leaves behind questions. In the immediate aftermath, attention naturally turns to visible outcomes: cities liberated, armies defeated, flags raised. Yet beneath these symbols lies a less visible legacy, one shaped not by combat alone, but by the industrial and scientific responses to wartime constraint. The fuel that carried the war to its conclusion does not disappear with peace. High-octane aviation gasoline, once an emergency requirement, becomes a structural component of post-war aviation planning. The techniques refined under pressure, catalytic cracking, alkylation, isomerization, reshape the petroleum industry. Refineries that once prioritized volume increasingly prioritize control and consistency. Quality becomes an operational requirement, not a luxury. Civil aviation inherits the benefits. Aircraft fly higher, farther, and with greater reliability. Jet propulsion, emerging from wartime research, will soon impose even stricter demands on fuel composition and stability. Methods developed for survival in war become standards for safety in peace. The individuals who made this transformation possible rarely appear in victory parades. They are chemists trained to think in reaction times and pressure ranges, engineers who learn to treat failure as data rather than defeat, refinery workers who labored through nights illuminated by floodlights, aware that a single error could ground aircraft thousands of miles away. One Standard Oil engineer, interviewed years later, described the task without ceremony. "We didn't build airplanes. We made sure they could be used as intended." The war forced American planners and industries to confront an uncomfortable reality. Industrial capacity alone does not guarantee readiness. Abundance without precision creates vulnerability. Innovation begins not with confidence, but with the recognition of limitation. In 1941, the United States entered the war without sufficient quantities of the fuel its most advanced aircraft required. By 1944, it was supplying not only its own forces, but those of its allies. That transformation did not occur spontaneously. It resulted from coordinated policy, accelerated engineering, and a willingness to discard familiar methods when they no longer met operational demands. This is the enduring lesson. Modern war is not decided by courage alone, though courage remains essential. It is shaped by systems, by the alignment of science, industry, logistics, and strategy under sustained pressure. Often, the smallest components impose the greatest constraints. Octane ratings do not appear on monuments. Catalysts do not receive medals. Yet without them, the skies over Normandy, and many battles beyond, would have unfolded very differently. For those who lived through the war, these truths required little explanation. They had seen how quickly assumptions failed and how rapidly adaptation could restore capability. That experience informed the post-war world, shaping institutions designed to anticipate limitation rather than deny it. Today, as those wartime airfields recede into history, the lesson remains relevant. Power is never simply a function of strength. It is a function of preparation, of understanding what enables performance and what must change when reality imposes new demands. In the end, the air war was not won by chance. It was sustained by learning, adaptation, and timely action within systems that recognized their own constraints. And inside every engine that carried the war toward its conclusion burned quiet evidence of a broader truth. When necessity exposes weakness, innovation, properly directed, can alter history without ever appearing on the battlefield.